welcome back everyone. So we've had a really long break in this project. Let's just see. We are going. This should be working. I'll have to bring myself back to everything we had done before, and the setup we had before. Just very quickly double checking that everything is working. I'm actually just gonna let's see if things are working. Yep, everything is working. Everything is working. I actually just needed to check. I checked on my phone. So we are back for Extremely Open Science this year. I do want to keep this project alive. We had a big break last year. There were several events towards the end of the year that made it hard to continue streaming every week. So we had the big grant deadline in November, and then also in my group. So for a bunch of different reasons, actually not reasons that have nothing to do with each other, it just so happened that a lot of things came together in November. So a lot of things that are completely unrelated between several different people joining the group. We also posted our update newsletter. I'll show it in a second. Actually, maybe let's do the. Yeah. So we have it's a little bit. Yeah. So we have this update newsletter that we put out regularly. I'm gonna put it in the chat as well. And one of the things that happened was that so actually Anil arrived a little bit earlier, but then Alexandre, Kruti, and Juan, they both arrived more or less at the same time. You had this grant proposal due more or less at the same time. We had a couple of visitors, so Marcus and Etienne both visiting at the same time, and this meant that a lot of things were happening in this October-November time, and then when December comes around, that's close to Christmas, and so the last few months of the year were very difficult, very busy, and the Sardine project, Extremely Open Science project, kind of fell a little bit by the wayside. So, however, having said that, I still think that it's a great idea, great project. I think the science is there in the sense that I'm now convinced that I should put the microphone close to my face. I'm now convinced that there is something to the idea. I don't think we've managed yet to completely. Still making these adjustments. Oh, yeah, we're up. We have not yet completely nailed down. Yeah, this is the project, or this is the exact formulation of this idea. But I think there's a there. So this is what we'll be looking at for the next few months, and hopefully, eventually getting an actual tool and then an actual publication, right? And so today, again, everything we have is online. Everything. So the code is online on GitHub. There's obviously I'm posting here. I have really not looked at this yesterday. I was a little bit tempted to go back to it yesterday and just make sure that we would, I would have some refresh in my mind, but I didn't. And so today I'll just go and look at it fresh. All right, so maybe without further ado, I'm a little bit rusty. I forgot to play the intro music. So let's play the intro music now. There you go. Now we have the intro music, right? Yeah. So even this type of stuff, like what's the muscle memory control of? Okay, this is how you play the muscle. This is how you play the intro music. Was a little bit rusty. All right, let's go back to the code. Sorry. So here we are. So this is the Sardine project, and I am going to. Oh, I see what I did there. Let me actually give me 2 seconds. I'm going to fix something real quick. something real quick. I'm gonna change the okay. All right, so I've changed it so that now I am looking at the camera when I'm looking at the right screen, right? All right, so this is oops, sorry, 1, 2, 3, forgot. All right, okay, as I said, I'm a little bit rusty with this stuff. All right, so this is what we left off. So, all right, so this is copying, readme, there's some notes, so some stream notes. Okay, yep, so again, September, October, and then things sort of started to okay. Okay, so to start from the very beginning, right? The goal of the Sardine project is that we observed empirically, and we'll have a paper probably soon with some of this data as well, at least a preprint. I mean, that when we have genomes, and specifically metagenome assembled genomes, so MAGs, that come from nanopore data, so Oxford nanopore data, they have a different error profile than genomes that come from Illumina data. In particular, they have more of these small indels, so missing letter here and there. And one of the things that causes is that causes genes to break, and so we end up with more apparent pseudogenes. And we've throughout this project we've called them pseudogenes or apparent pseudogenes or artifactual pseudogenes. So a pseudogene is a real biological thing where you have often the fossil of an actual gene that for some reason or another is no longer functional. And so what we have is something that biologically the gene is there, but through some error in the process, so in this case mostly because of the sequencing, in the assembly we have the gene is not there, so it's an apparent pseudogene, right? And so we've been playing around with this idea with the ultimate goal of developing some tool that could take a MAG and could spit out some metric of, oh, this is a good genome, or no, this is a bad genome because we think it's bad because it has too many pseudogenes, right? Or more pseudogenes than we would expect. Right. So let's see what we can do about it. Right. So we had started to work. We started to work with simulation data. So we ran this. No, oops. Let me. So I'm gonna really quick sort of update my lazy plugins for NeoVim so that we don't get that message. So we worked with progenomes data. So we got some of these, E. coli K12, Bacillus subtilis, Listeria monocytogenesis, Campylobacter jejunum, Staph aureus. So we downloaded these things from progenomes. So this should be the reference genomes that we're going to use for now. So this we've done. Sorry, okay. This is all there, and then we simulate adding mutations, and so okay. So and this is still maybe one area where we really need to improve things, which is this mutation model is very, very simplistic, right? So so the mutation model here, we choose a position, and then with 40% chance, we add a base pair, we remove a base pair, or we substitute a base pair with 20% chance. Right, so this is not great, but probably does the job for now. And then okay, and then DNA. Okay. Okay. It's probably some code there we need. No. And then we ran checkm2 on all of these. I guess this some exploration there. Okay. Okay, so, and then we had some plots. Okay. Okay, so this is what we've been playing with, right? And then, so we started with doing 50,000 mutations, which is, frankly, an absurd number, right? We don't need that many, and it's not a realistic number of mutations. But but it's probably good to start with something extreme. Right, this is what we would see. So this is with E. coli. Okay, this goes up to. So we had started with 50,000, just as something very extreme, just to prove the point, and now we turned it down to 5,000 as probably, low thousands is probably the range that's realistic to expect, right? And so, right, so here's what we see with E. coli K12, so 0 mutation. So this is the reference strain, and the average gene size. So this is in nucleotides. I mean, I think it's nucleotides because so that the numbers make sense. So this is about 300 something amino acids. That makes sense. Average gene size. As the number of mutations goes up, the average gene size starts to go down quite rapidly. So genes are starting to get interrupted almost immediately. So even with few hundred mutations, there's already some, and then completeness as estimated by checkm2 starts to go down and crosses, sort of the 90% threshold about here. So this is still very much the range, a realistic range. So this is, so for example, in some of the data that I alluded to, that we have real data that sees this effect, we actually have hybrid data, meaning that we have both nanopore and Illumina data, and so we can use the Illumina data to polish the nanopore data, and what we see is that the completeness then goes up by quite a lot. And so the message is actually a little bit more subtle than that. So if we have for deeply sequenced, if we have a lot of depth for a particular organism, then actually the Illumina data doesn't add that much. But for organisms that are at lower depths, where we can still assemble them, but we assemble them with a lot of errors, and then the Illumina data brings the completeness way up. Adds, this here would add, 15 percentage points of completeness. That's on the higher end that we observe, but we do observe this type of effect so probably going for the thousands of mutations to actually, that's a good idea. Well, it's a good idea because we could use those data to quantify the number of mutations. So basically that would be the difference between the difference between the polished and unpolished. So that's actually a good idea. I should check that. Yeah. So okay. So I wrote that down. So all right. So we have here. Yep. So this is where we started off. actually, this is the, we have, with nanopore data, we see lower completeness. And it's important to note that CheckM2 and actually CheckM1 was the same. These are gene-based tools. So the completeness that they estimate is not the completeness of the, how many base pairs you have in some sense, but the completeness of the gene set, which in the with Illumina data is more or less 1-to-1 between those things. But with nanopore data, you can have blocks of genome that are there, but they're missing the genes because the genes are again, they're messed up because of these small indels, right? Okay, so this is what we looked at. All right. Okay, and then we did a bunch more things, right? Let's see where. What was this? Okay, let's remove this. Okay, is the simulation done? Yep. So, okay. And then we were working on this length by KO file. All right, so today I'm mostly trying to get my head back into this. Okay, right. So a bunch of imports. So we've been very, very heavily using Jug here. So Jug is this Python-based framework that we have to basically run things and potentially using multiple processors even on the cluster. But here in this project, I said before, I'm running everything on my laptop, which is admittedly a nice laptop, but everything, if you have, basically if your laptop is good enough that you can run YouTube, then okay, then this is fine. Okay, this is Right, so nowadays, and things have actually changed so fast. We've been doing a lot of computation here at QUT, and and we, with the clusters and the machines we have nowadays, we can do things in hours that would have taken us months, or things in days that would have taken us months. For example, here we're looking at the GMGC. And GMGC, just see, the GMGC is 10,000, or GMGC is 13,000 samples. This used to be a very, very, very large number. This took about almost a year of just compute, basically. And nowadays, 10,000 metagenomes is not even that much. Right? All right, but still, we still use it. Still, I think for its purpose, it's still, I think, the largest data set out there in terms of having, it's a collection of all of the genes from all of these metagenomes across, across all habitats. It was basically everything that was available when we started the project, and we keep updating. We have not updated the GMGC itself, unfortunately. That's work in progress. But we have updated, for example, we have Spire now. We have Spire. Which Spire? We have Spire. Where we have 100,000 metagenomes, and this we keep updating this. Right. All right. So let's see. Okay. Let's see what we're doing here. All right. So we loaded this output GMGC complete annotated. Where does this come from? Complete. Okay. Run GMGC daemon. So So we ran something called run GMGC diamond. Okay. Okay. All right. So GMGC. So this was GMGC 10. So this is supposed to. This is not 10. This is 1 dot, more like 1.0. 95% non-redundant. Complete is complete genes only. So this was actually one of the internally contentious, including with some of the reviewers, whether to include or not include the fragment genes in the GMGC. In the end, our attitude is that we start with including everything, and then we also provide these subsets that only include certain subcategories. In this case, only the complete genes. All right, so run diamond. Okay, so we are running the same diamond as checkm2. I think these are the same. Yep. Okay, so split FASTA file. All right. Okay, so we split the FASTA file, the GMGC, in chunks of 2 million, and then we run diamond on each chunk. Oh, annotate with orf lengths. Okay. All right. Okay, makes sense. Sorry. All right, this makes sense. Let's go back here. Okay, we load this. Okay, we get the KOs. Okay. I'm sorry. Okay, number of sequence. Okay. Okay. Sorry, I need to add this magic thing at the top. Trying to remember everything that was here. Okay, so E. coli K12. So again, all of this code is on GitHub, so I'm not doing anything. So I'm just, where is it? Yeah, so I'm just going over the code that's here in length by KO and trying to remember, trying to get my mind back into it. Okay, so we're the okay, good. Okay. Sorry. Okay, sorry, this. Okay, no, just fixing this. Let's just fixing this warning. Oh. Sorry, I'm a little bit. Okay. Okay. No. Sorry. Sorry about that. I meant to. Did not meant to. Okay. Okay, I guess these scores are empty. Okay. Okay. Oh. Okay. Something here is messed up. Okay. Now this will work. Okay. Okay, so, all right, so voila. Okay. All right, yeah. So this is so this is the thing, right? As we increase the number of mutations, we have an excess. But even with 0 mutations, we do have some extreme values already. So that's the thing we wanted to get. Yeah. Yep. All right. This is okay. Okay. Yes, I remember. This is where we left off. So z-scores, right, Balim. Okay, so, all right, so the values below the limit, group by number of mutations, some, okay, and so, doesn't work. Okay, yeah, this is the more. Okay, all right, this is what we had before. I remember this, right? So if this is a z-score limit, then, you know, if we take -10, then the wild type only has 2, but it goes up to 3 and 4, which is not a huge thing. I think the biggest differences are actually a little bit like here. Still not great. Okay. All right. Okay, so attempt to find chaos George. Alright, so attempt to find chaos with very stable gene sizes. So that's actually not a bad idea. I mean, I think, or right, for example, that's nice. K0 for, this is nice. So this one, okay. Are these the ones that, yep, okay. So just, let me just check. Okay, just out of family. Okay. Okay, I actually want to look at this. Sure, let's save it. Okay. Okay, so there it is. How do I read this? There's no header. That's subject identity, alignment length, mismatches. Okay, all right, let's do this again. Okay. So subject identity, alignment length. So if I think the identity was 100, so we probably one of the versions in the, so here we're using E. coli K12, and probably one of the versions on the database is the E. coli K12. Right? We probably have this exact strain, and gene in the database. So there's probably, it's not a surprise there that we have. Yeah, that would. Right. Okay. So let's just load this again. I think this is the other one that we were looking at before, but okay, let's look at this one. There's no show. There's squeeze? No. I want to see the whole. Okay. Okay, so let's see. This. This is just a perfect alignment to this thing, which is probably just the. Doesn't from 0 to 12. Or from position 1 to 212, perfectly aligned, right? Okay. Okay. Okay, actually not. This is interesting. Wait. Oh. Okay. All right. This is maybe not great. What this means is that this is, so 212 really is the smallest thing we've observed in the complete gene. I guess yeah, this is not great, because intuitively I would have said, oh, look, this KO actually seems very stable in size, and except for a few outliers, it just happens that, interestingly, that outlier is this is E. coli K12. Okay. Let's look at the other one. Okay, this is not. Okay. Just look at it. Okay, all right, this one again. Okay. Okay, 46. Okay, I think this is amino acid, so it's small protein. It's our favorite type of protein. 46, all right. And okay, all right, at least here it's not. Wait. So the mean is 46, so wait. This scarce filter. Oh, right, let's. Okay. Okay, so this is the KO that was looking weird. Okay. 227 to 3. Okay. See. Okay. Again, not that. Doesn't seem that spread out. Okay. This was 148. Okay, again, I think this is, we are getting it back. Okay, we are getting it. Again, we have the exact sequence in the database, so obviously we get it back. Still a predicted protein, interesting. That, you know, that there's no, okay. But if I look at the GMGC, interestingly, (148) is way below. All right, so this seems like, all right, this seems like this would actually be a bona fide pseudogene, or at least in this something that. Right, nothing else. There's no other gene that's anywhere near as small as this one is. That is 148 amino acids. They're all significantly larger. This KO even seems, 400. We have 455 of them, examples, and they're all in the range of 227 to 300 amino acids, and actually, so if you look at the, so the 10th percentile. So the 5th percentile is 247 and the 95th is 266. So that's actually a tight range, much tighter than some of the other ones we've seen. And so, so if we saw something that was 148, I would say, that doesn't sound right. Something went wrong there. Okay. Okay, 148. All right. I have to say, not enthused about this. Okay, let's write down some notes and wrap up for now. So, okay. Okay, so okay. In E. coli, all right, since recover the Okay. Copilot is messed up here in terms. Okay. Okay, it's in, yeah. Interesting. Interesting, not great, but interesting. All right, so let's put that notes. Okay, it was for the other one, for KO 1232. So this was not as clear that this was the right thing. But okay. Okay, let's do this. Yep. Okay. Okay, let's just wrap up here. Stream notes. What am I looking for? Yeah, but okay, let's just. Okay, this we're not keeping. Yep. Okay, let's keep this. All right. So small factors update. Update deprecated code. Small visual. Okay. Okay, let's do this. Push. So everything, yep, everything is now online. So everything is online. Everything is at these on GitHub. So I'll be posting a recap a bit later. So this week there's less to recap. We didn't make that much progress. It was mostly about getting back into the game of figuring out what's going on, what all of this code is about. But we did learn again that it's maybe not so easy. Maybe this is not so easy, because this E. coli, it seems that yes, this E. coli genes do seem to be much shorter than the ones we get in the GMGC. So yeah, maybe something's going on there as well. Maybe these are some real pseudogenes, not apparent pseudogenes, right? Those do exist. So if we're looking at the outliers, we looked at the two that look the worst. So maybe that's what it was. So let's leave it there. Let's keep going next week. Maybe trying to understand, what it seems that it's this middle range, so not the most extreme outliers, but this z-score around -6, where we really saw bigger separation between what we saw in the wild type versus the mutated version. So let's see if I now remember to play the outro. There it is. I'm playing it, and I will see you next week. So be well and see you next week.